So now we're on section 4, second order determinants. As I said in the previous video, the determinant is yet another way to solve for simultaneous equations. The determinant creates an array of numbers. These numbers correspond to coefficients and constants, okay? And if we look at the values here, you can see we've replaced numbers with these coefficient values A1 and A2, B1 and B2, and then our constants are K1 and K2. Okay, so these numbers correspond to those coefficients and constants as of a set of equations that describe the physical system, such as an electronic circuit. And the idea behind this is we can kind of mechanically solve for these unknowns. And this actually makes a great way of solving for systems in a computer setting. You could even set this up in Excel to do your calculations. And sometimes there are canned programs that have these values set up in the array for you. So as an example, if we have a circuit that contains two current paths, we can write what we've learned about Kirchhoff's equations for each of those paths. If there's just two unknown values, we can use the determinants then to solve for equations to find the values of the two unknowns. So our two unknowns are still the x and y, as you can see in these two general equations. So A1, B1, A2, B2 are the coefficients that we normally see as number values, and K1 and K2 are the constants that we normally see in our previous examples as constants. Notice that the equations are set up the same way that we set them up when we use the addition and subtraction method. After the terms of the equations have been arranged in this way, we can find the values for x and y. So when you first look at the arrays as they're depicted here in the bottom of the page, they might look a little strange to you, but as you work through with them, you will see that they have some great ways of solving the problems by going stepwise through the process. So you can see here for x, we solve by creating a numerator and denominator in our matrix, numerator and denominator wise, and the same thing for y. And we can take these apart and create the mathematical expression by doing sums and differences and products. So in this case, as we will see as we go on, K1 and B2 are arranged as a product. K2 and B1 are arranged as a product. A1 and B2 are arranged as a product. A2 and B1 are arranged as a product. And in each case, they become the difference. So in analyzing these equations, the array of four variables in the denominator is called the determinant of the denominator. The determinant then has two rows and two columns and is called a second order determinant. The numbers A1, A2, B1, and B2 are called the elements of the determinants. So when we decompose the arrays then into these products difference, this difference of products, A1, B2 minus A2, B1 is called the expansion of the determinant. The numbers A1 and B2 are the principal diagonal. The numbers A2 and B1 are the secondary diagonal. The expansion of the determinant results from the product of the elements in the principal diagonal A1, B2 minus the product of the elements in the secondary diagonal A2, B1. So if we look at it illustratively, you can see that we've got those relationships, A1, B2, A2, B1, and we take the difference. This is the denominator for both unknowns. So let's roll back here. Well, if you take a look, that denominator and that denominator for x and y are in fact the same. It's the numerator that has different terms, okay? And you can see we've got B2 on the right, K1 and K2 on the left, and in the y version, we've got K1, K2 on the right, and A1, A2 on the left. Okay, so the determinant for the numerator of the unknown x is written, as we just showed, Here we have replaced A1 and A2, the coefficients of the first unknown x, with the constants K2 and K1 from the right side of the equations. The determinant of the denominator of the unknown y then is written. So you can see they look similar, but you've got b terms and a terms in each case. Here we replaced in the second one, b1 and b2, the coefficients of the second unknown y with the constants from the right side of the equations. So that's all pretty much the setup for second-order determinants. We can recap this to say the steps for solving simultaneous equations using determinants are: 1, to arrange the terms of the equations with the unknowns on the left side and the constants on the right side. Second, arrange the unknowns so they appear in the same order for each equation. The third step, use the coefficients of the unknowns to form an array of the numbers called the determinant of the denominator. For each unknown, in step 4, create an array of numbers similar to the above array, except substitute the constants from the right side of the equations for the unknown coefficients. This is called the determinant of the numerator. Step 5, the value of each unknown can then be calculated by dividing its determinant of the numerator by the common determinant of the denominator. And then finally, check your answers and substitute the solutions into the original equations and confirm the equalities. So through use, you will get used to these steps. They're really not that difficult. So when we learn in our electronics classes how to do simultaneous equations to solve for current loops and voltage branches and nodes, this will become very, very important. So right now we're just going to learn the rudimentary process of using a determinant. Okay, so when we come back, we're going to look at this example 416 and use those relationships that we saw previously to solve one more time using a determinant.